You think splitting an atom releases energy because you're breaking something, like smashing a rock, like tearing paper, apply force, break bonds, release whatever was held together. That's the intuition. That's what most people imagine. But that intuition is completely wrong. Splitting an atom doesn't release energy because you're breaking it. Splitting an atom releases energy because you're converting mass into energy. You're taking matter, physical substance, and transforming it directly into pure energy. And the amount of energy released is so absurdly large, so incomprehensibly beyond anything in your everyday experience, that it defies belief. Except it's real. We've done it. We've measured it. We've weaponized it. And when you understand what's actually happening when an atom splits, when you trace the process from nuclear structure to mass conversion to explosive release, you discover something profoundly disturbing about the nature of matter itself. What you think of as solid, stable, permanent is actually a compressed spring, a frozen explosion, a pattern of energy held together by forces, containing within it the potential for catastrophic transformation. Let me show you exactly what happens. Start with uranium, uranium-235 specifically. A large, heavy nucleus, 92 protons, 143 neutrons, all packed into a space smaller than a trillionth of a meter across. This nucleus is barely stable. The protons repel each other electromagnetically, like charges repel. 92 protons, all positively charged, all pushing against each other with enormous force. The electromagnetic repulsion is trying to tear the nucleus apart, but the strong nuclear force holds it together, just barely. The nucleus sits in a precarious balance, stable but only just. Now send in a neutron, a slow neutron. It approaches the uranium nucleus. The neutron has no charge, so it doesn't feel electromagnetic repulsion. It can get close, it can penetrate the nucleus, and when it does, the nucleus absorbs it. Uranium-235 becomes uranium-236, and uranium-236 is not stable, not even close. The addition of one more neutron tips the balance. The nucleus can't hold itself together anymore. The electromagnetic repulsion wins. The nucleus deforms, it stretches, it elongates into a dumbbell shape, and then it splits. Two smaller nuclei fly apart, usually barium and krypton, though the exact fragments vary, plus 2 or 3 free neutrons. This is fission, the splitting of a heavy nucleus into lighter fragments, and it happens in about 10 to the 20 seconds, 100 trillionth of a second, essentially instantaneous. One moment you have uranium-236, the next moment you have barium, krypton, and neutrons flying apart at 3% of the speed of light. Now here's the question, where does the kinetic energy come from? The fragments are moving fast, very fast. They have enormous kinetic energy, about 200 million electron volts per fission event. That's about 3 times 10 or 11 joules. Doesn't sound like much, but that's per atom. And there are about 10 to 24 atoms in a kilogram. If you could fission every atom in 1 kilogram of uranium-235, you would release about 8 times 10 to 13 joules. That's 20 million kilowatt hours. That's enough energy to power a large city for a day, from 1 kilogram. But where does this energy come from? It's not chemical. Chemical reactions involve rearranging electrons around nuclei. The energies are tiny compared to nuclear reactions. Burning 1 kilogram of gasoline releases about 50 million joules. Fissioning 1 kilogram of uranium releases more than 1,000,000 times more energy. This is not rearranging molecular bonds. This is something fundamentally different. The energy comes from mass, from the conversion of mass into energy. Einstein's equation, E equals mc squared. When the uranium nucleus splits, the total mass of the fragments is slightly less than the mass of the original nucleus, about 0.1% less. That mass didn't disappear into nothing. It converted into kinetic energy, into the motion of the fragments, into radiation, into heat. Let's be precise about this. One uranium-235 atom has a mass of about 235 parts 44 atomic mass units. When it fissions, the typical fragments have a combined mass of about 234.810 atomic mass units. The difference is 0.234 atomic mass units. That's the mass that converts to energy. And 0.234 atomic mass units is about 3.9 times 10 to the 28 kilograms. Multiply by c squared, you get 3.5 times 10 to the 11 joules. That's the energy released per fission event, and it matches the measured kinetic energy of the fragments exactly. This is not approximate. This is not close enough for practical purposes. This is exact. The missing mass equals the released energy divided by c squared. Always. Every time. The equation is not a prediction, it's a measurement. We weigh the nucleus before, we weigh the fragments after. we measure the energy released, and the numbers match perfectly. Mass is being converted to energy. Now think about what this means. The mass is not being destroyed. Mass is energy. They're the same thing. The nucleus before fission contains a certain amount of energy locked up as mass. After fission, some of that mass energy has been converted to kinetic energy. The total energy is conserved, but the form changed. What was rest mass became kinetic energy. What was locked in nuclear structure became motion. And here's what makes this terrifying. The amount of energy is enormous because of that c² term. The speed of light is 300 million meters per second. Square that. You get 9 times 10 power 16. That's the conversion factor. Every kilogram of mass is equivalent to 90 million billion joules. Even a tiny amount of mass converts to an absurd amount of energy. Losing 0.1% of the mass of 1 kilogram means releasing 90 trillion joules. That's the energy of a small nuclear weapon. This is why nuclear weapons work. Not because they're using exotic reactions, not because they're tapping into some mysterious energy source, but because they're converting a small fraction of mass directly into energy. And because c² is such an enormous number, even that small fraction produces catastrophic results. But there's more. When a uranium nucleus splits, it doesn't just release energy, it releases neutrons. 2 or 3 free neutrons per fission event. And these neutrons can go on to hit other uranium nuclei. Each neutron can cause another fission, which releases more neutrons, which cause more fissions. This is a chain reaction. Exponential growth. 1 fission becomes 2, 2 become 4, 4 become 8. The number of fissions doubles every generation. How fast does this happen? Neutrons travel at about 2% of the speed of light when they're released. In a block of uranium, they'll hit another nucleus in about 10^8 seconds, 10 nanoseconds. So the doubling time is about 10 nanoseconds. Start with 1 fission. After 10 nanoseconds, 2 fissions. After 20 nanoseconds, 4. After 30 nanoseconds, 8. After 80 generations, about 800 nanoseconds, less than a microsecond, you've fissioned every atom in a kilogram of uranium and released the full 8 times 10 power 13 joules, all in less than a millionth of a second. This is an atomic bomb, a runaway chain reaction. Exponential energy release happening faster than the material can expand. The energy is deposited so quickly that the uranium becomes a plasma. Temperatures reach millions of degrees. Pressures reach millions of atmospheres. The plasma expands violently, faster than sound, a shock wave, a fireball, thermal radiation. Everything within hundreds of meters vaporizes. Everything within kilometers burns, all from converting less than a kilogram of mass into energy. But here's what most people don't understand. The bomb is not special. The uranium is not special. Every piece of matter contains this energy. The difference is that uranium-235 is one of the few nuclei that's large enough and unstable enough that you can trigger a chain reaction. Most atoms are too stable. You can't split them by hitting them with neutrons. The strong nuclear force holds them together too tightly. But the energy is still there, still locked in the mass, still waiting. Take a rock. Any rock, 1 kilogram. If you could convert all its mass to energy, you would release 9 times 10 power 16 joules. That's 21 megatons of TNT. That's more than the largest nuclear weapon ever detonated by the United States. A rock, a piece of granite or limestone or sandstone, contains enough energy to level a mountain range. Not because rocks are special, because mass is energy, and rocks have mass. But you can't access it. Not easily. The atoms in a rock are stable. Carbon, silicon, oxygen, aluminum. Their nuclei are tightly bound. You can't fission them. You can't make them release their energy through simple splitting. The barriers are too high. The forces are too strong. The energy is there, but it's locked away behind structural constraints that everyday circumstances cannot overcome. This is why the world doesn't explode. Why matter is stable. Why you can hold a rock without it detonating. The energy is there, enormous energy, but it's trapped, frozen into nuclear configurations that resist casual disruption. Mass is not passive substance. Mass is compressed, restrained, barely contained energy, and the restraint is what allows anything to exist. Now let's understand where this energy actually comes from. Why is the nucleus after fission lighter than the nucleus before? What happened to the missing mass? The answer is binding energy, nuclear binding energy. The energy that holds the nucleus together against electromagnetic repulsion. Think of it like gravity. If you have a rock on a cliff, it has potential energy. gravitational potential energy. If the rock falls, that potential energy converts to kinetic energy. The rock speeds up. By the time it hits the ground, all the potential energy has become kinetic. The total energy is conserved, but the form changed. Nuclear binding energy is similar, but backwards. When protons and neutrons come together to form a nucleus, they fall into a potential well created by the strong nuclear force. They release energy. This energy leaves the system as radiation or kinetic energy of other particles. And because energy has mass, losing energy means losing mass. The nucleus has less mass than the separated protons and neutrons. The mass difference is the binding energy divided by c squared. For uranium-235, the binding energy per nucleon is about 7.6 million electron volts. For the fission fragments, barium and krypton, the binding energy per nucleon is about 8.4 million electron volts. The fragments are more tightly bound. They have more binding energy, which means they have less mass per nucleon. The difference, about 0.8 million electron volts per nucleon, is the energy released as kinetic energy during fission. This is why fission works. Heavy nuclei like uranium have less binding energy per nucleon than medium mass nuclei. If you split a heavy nucleus into medium mass fragments, the fragments are more stable, more tightly bound. They have more binding energy. And that extra binding energy comes from somewhere. It comes from mass. The mass decreases. The binding energy increases. And the difference is released as kinetic energy. But here's the thing that breaks intuition. The nucleus is not a bag of marbles. Protons and neutrons are not sitting inside like objects in a container. The nucleus is a quantum system, a bound state of quantum fields. The protons and neutrons are wave functions, probability distributions. They overlap. They interfere. They're not localized in the way you imagine. And their mass is not just the sum of their individual rest masses. Most of their mass comes from the kinetic energy and field energy of quarks and gluons inside them. The nucleus is a pattern of energy, a stable configuration. And when that configuration changes, the energy distribution changes. The total mass changes. This is what E equals mc squared really means. Mass is not a fixed property of particles. Mass is energy, the energy of fields, of motion, of interactions. When you change the configuration, you change the energy distribution. And changing the energy means changing the mass. The uranium nucleus has one mass. The fission fragments have a different total mass. The difference is the energy released. But the energy was always there. It was the mass. The mass was the energy. They're not two things that convert into each other. They're the same thing in different forms. Now let's make this even more explicit. Where does most of the mass of a proton come from? A proton is made of 3 quarks, 2 up quarks and 1 down quark. The up quark has a mass of about 2 million electron volts. The down quark has a mass of about 5 million electron volts. Add them up. 2 ups and 1 down gives about 9 million electron volts of quark mass. But the proton's mass is 938 million electron volts. Where does the other 929 million electron volts come from? It comes from the gluon field, from the kinetic energy of the quarks, from the interaction energy. The quarks are moving at relativistic speeds inside the proton. They're constantly exchanging gluons. The gluon field is fluctuating. All of this energy contributes to the proton's mass. About 99% of the proton's mass is field energy and kinetic energy. Only 1% is the intrinsic rest mass of the quarks. The proton is not 3 particles sitting together. It's a bound state of quantum fields. And most of its mass is the energy of those fields. This means that when you split a nucleus, when you rearrange protons and neutrons into a different configuration, you're changing the field energy. You're changing how the quarks and gluons are distributed. You're changing the binding energy of the system. And because mass is energy, changing the energy means changing the mass. The fission fragments have a different field configuration than the original nucleus. That different configuration has different energy, different mass, and the difference is released. This is the deep truth. Mass is not substance. Mass is structure. It's the energy cost of maintaining a particular configuration of fields. Change the structure, change the energy, change the mass. And if the new structure is lower in energy, more stable, more tightly bound, the excess energy is released. That's fission, that's fusion, that's every nuclear reaction. not breaking things, not destroying matter, but rearranging field configurations and releasing the difference in binding energy as kinetic energy. And this applies to everything, not just nuclei, not just uranium. Every object has mass. Every object is a configuration of quantum fields. Every object contains energy equivalent to its mass times c squared. A coffee mug contains about 10^17 joules. A human body contains about 10^18 joules. A car contains about 10^20 joules. All of this energy is real. All of it exists. All of it is there in the mass of the object, not as potential energy that might be released, but as actual energy that is the mass. But accessing it requires changing the field configuration, requires rearranging the quarks and gluons and electrons into a lower energy state. For most objects, this is impossible. The atoms are stable. The nuclei are tightly bound. There's no easy way to release the energy. The barriers are too high. The forces are too strong. The energy is locked away, inaccessible, trapped in configurations that resist change. Uranium is different. Uranium-235 is barely stable. Its nucleus is so large, so packed with protons, that the electromagnetic repulsion is almost strong enough to tear it apart on its own. You don't need to add much energy, just a single neutron, and the nucleus can't hold itself together anymore. It splits, and some of the binding energy is released, not all of it, just the difference between the binding energy of uranium and the binding energy of the fragments. But that difference, small as it is in percentage terms, is enormous in absolute terms because c squared is so large. This is the mechanism. This is what's happening. The neutron enters. The nucleus becomes unstable. The balance between strong nuclear force and electromagnetic repulsion shifts. The nucleus can't maintain its configuration. It deforms. It splits. The fragments fly apart, driven by electromagnetic repulsion. As they separate, they convert binding energy to kinetic energy. The mass decreases. The speed increases. And the energy released is exactly the mass difference times c squared. And this is not theoretical. This is measured. We can weigh uranium before. We can collect the fragments after. We can measure their masses. We can measure their velocities. We can calculate their kinetic energies, and the numbers match, always. The mass energy equivalence is exact. The energy released equals the mass lost times c squared to within experimental precision. The equation is not an approximation. It's a fundamental relationship. Mass is energy. Energy is mass, and nuclear reactions prove it directly. Now think about the implications. Every object around you contains enormous energy. The desk, the wall, your phone, your body, all of it is compressed energy. All of it is held together by forces. All of it could theoretically be converted to radiation if you could overcome the barriers. A pencil contains enough energy to level a city block. A glass of water could power a nation for a year. A human body could devastate a continent. All of this energy is real. All of it exists, right now, in the mass, waiting. But it's inaccessible, and that inaccessibility is structural. It's not that we lack the technology, it's that the laws of physics create barriers that prevent spontaneous conversion. The strong nuclear force binds nuclei. The electromagnetic force binds atoms. These forces are strong. The energy wells are deep. Getting from one configuration to another requires overcoming large barriers, and for most atoms, those barriers are too high. You can't split them. You can't fuse them. You can't make them release their energy except under extreme conditions. Uranium is one of the rare exceptions, a nucleus large enough and unstable enough that a single neutron can trigger disintegration. And even then, only a tiny fraction of the mass converts to energy, about 0.1%. The rest remains as mass in the fragments. If you could convert 100% of the mass to energy, if you could completely annihilate matter, the energy released would be 1,000 times larger. But we can't do that, not with fission, not with any known practical mechanism except matter-antimatter annihilation, which requires antimatter that we can't produce in useful quantities. So we're left with fission, and fission is already terrifying enough. 1 kilogram of uranium-235, fully fissioned, releases 20 kilotons. That's the yield of the Nagasaki bomb. That's enough energy to destroy a city. From 1 kilogram, from converting 0.1% of its mass to energy. If you could convert the full mass, 1 kilogram would release 21 megatons, 1,000 times more. But you can't. The barriers prevent it. The laws of physics protect you. And this is the paradox. Matter is energy. enormous, concentrated, catastrophic energy, but it appears solid, it appears stable, it appears safe, because the forces holding it together are strong enough to resist casual disruption. The world is stable not because energy isn't there, but because it's trapped, frozen, locked into configurations that resist change. And those configurations, those patterns, are what we call matter. But the patterns can break. Given the right trigger, the right conditions, the barriers can be overcome. The nucleus can split, the mass can convert, the energy can be released. And when the frozen form melts, when the compressed spring uncoils, the results are catastrophic. Not because something magical happens, but because E equals mc squared, because mass is energy, because the solid world is a lie, because everything you see is compressed violence held in check by forces barely strong enough to contain it. This is what splitting an atom means, not breaking a particle, but forcing a rearrangement, a transition from one field configuration to another, a release of binding energy, a conversion of mass to kinetic energy, a demonstration that matter is not substance but structure, not permanence but pattern, not reality but restrained explosion, and the only thing standing between calm and catastrophe is the strength of the forces maintaining the pattern. Every piece of matter is a frozen bomb. Every atom is a compressed star. Every object contains energy beyond imagination, not in some abstract, metaphorical sense, in a direct, literal, measurable sense. The energy is there, in the mass, right now, always. And the fact that you can sit calmly, holding objects, trusting their stability, is not because the energy isn't real. It's because the barriers containing it are strong enough to prevent release. Until they're not. Until you find a nucleus, like uranium. Until you provide the trigger. Until the balance shifts. And then the energy that was locked away, that was frozen into mass, that was trapped in nuclear structure, is released. All at once, exponentially, in a chain reaction that converts matter to motion in less than a microsecond. And the result is not a chemical explosion, not a rearrangement of molecules, but a transformation of mass into energy, a demonstration of E equals mc squared, a proof that matter is not what it seems, and a reminder that the solid world is built on a foundation of compressed energy, barely held together by forces that could, under the right conditions, fail catastrophically.